Pressure with depth. Here we've got what are called Pascal's vases. It's basically some glass tubes all connected at the bottom, and we can pour a liquid in here. We've got the wide tube, one with a zigzag, one with a lump in the middle, one off at a slope. What's going to happen when water is poured into this wider tube? We'll watch a video in a moment. Well, as you saw, the water reached the same height in all the tubes. That shows that at a given depth, the pressure is not affected by the shape or size of the container. If there was a greater pressure here, for instance, than here, then water would flow from the high pressure to the low pressure area. Here we've got a container of water with 3 holes, one at the top, one in the middle, one at the bottom. And this shows that in a fluid the pressure increases with depth. This point has got the weight of all this water above it pushing down, whereas this point has a greater weight of water. It's got all this water pushing down on it. And here there's an even greater weight of water, the entire container of water pushing down on the water coming out of this hole. We'll see a video of a real one in a moment. Okay, so the container has a cross-sectional area A, and at this height here, the pressure will be given by force over area, but the force is the weight of water, which is the mass of water times the gravitational field strength. But mass is density times volume, so basically the weight of the water will be the density times the volume times the gravitational field strength. And the volume is the height of this water multiplied by the cross-sectional area, the volume of a cylinder. So we get that the force is the height times the density times the area times the gravitational field strength. We can find the pressure then as the force, which we found here, divided by the area. The areas cancel, and we're left with the pressure at a depth h is given by h, the height or depth of water or fluid, multiplied by the density of the fluid, multiplied by the gravitational field strength. So for an incompressible fluid or a liquid, pressure is directly proportional to depth. The situation is more complicated in a gas, as density also increases as the pressure increases, so we'll look at atmospheric pressure in a future video. Water has a density of 1000 kilograms per cubic metre. So to find the pressure caused by a 10 metre depth of water, we can use this formula. Pressure is depth times density times gravitational field strength. At a depth of 10 metres, 1000 kilograms per cubic metre, gravitational field strength 9.81 newtons per kilogram, gives 98,100 pascals. This is close to the value of atmospheric pressure, meaning that just 10 metres below the water surface you experience twice the pressure that you experience on the surface. The extreme pressures found even further down can cause problems for divers and for submarine designers. What we see here is the force due to the pressure of water on the hull of a boat, and you find that as the pressure increases as we go deeper, the force increases. The horizontal components of the forces due to the pressure will act against each other. So basically this force has a horizontal component pushing this way, which is pushing against this force here pushing that way. That's causing to crush the hull, and boat hulls need to be very strong to resist this. The vertical components, so this force also has a vertical component, remembering from vectors of forces, we can convert this into a horizontal component and a vertical component by producing a triangle. The vertical components are pushing up on the boat, producing the upthrust. We'll be looking at upthrust in more detail in a future video too. Here we have a U-shaped tube filled with water, and as you can see, with just water the height is the same on both sides. But now we're going to see a video which will show that that's not quite the same when you have oil on one side. Here we have the tube with water and oil, and you'll see that the oil is to a higher level than the water. Oil has a lower density than water, so we need a greater depth of oil to give the same pressure at, say, this point. If the pressure was not equal at this point, the liquids would flow around until the pressure was equal at this point. And so we need a much bigger depth of oil, with oil having a lower density, to give that pressure, from pressure is H rho G, than we do with water with a higher density.